It does. I think I put the wrong room number.
Okay. Yeah, can you just tell the class?
Yeah. So the recitation for today's software lab is 319. 319 downstairs. It's not 418. I put on announcement. Sorry about that. So I will update the announcement as well. So yeah.
Yeah, thank you. Okay, so today we're going to talk more about the flow behind the aircraft, and then we're going to move closer and closer to the aircraft and look at the flow near the aircraft. Right, so this is a theme over most of the semester. So basically we'll keep zooming into the aircraft and look at more and more complex stuff. And this afternoon we are going to look at the software called AVL that actually just puts a lot of what we are learning today and a little bit of what we are learning next week into a software calculation. So we should be able to understand what it is doing inwards today. Okay, so we have been looking at the lifting line model. So we have primarily been looking before all these trailing vortex sheet, right? Basically far downstream of the airplane. So today we're going to look a little bit more in the scenario where there are not just the two vortices, but many vortices. And then we're going to be moving closer to the airplane and look at the effect of the bound vortex, right? So we have been thought of as we are so much further downstream that this bound vortex has no effect on the flow field, but like as we are moving closer to the airplane, the bound vortex will have an effect. Okay, so we explained the lift through conservation of momentum last lecture by only looking at the two wingtip vortices, and let me remind you of that. So on Monday we looked at what is the flow field everywhere, right? If we have two vortices, what is the formula for calculating the flow field of a single vortex? And once we add them up, we can calculate the velocity anywhere. And last lecture, we did the integral. We used the calculus to integrate over a vertical column the velocity field induced by this pair, the matched pair of vortices. And we're going to learn next week like why these vortices are matched in the sense that they have the same strength, the same circulation, but rotating in the opposite direction. Okay? And after we do the integral, we found that the total integral, right, over any vertical column is either having zero momentum if the column is outside of this pair of vortices, or have a vertical momentum, have a downward momentum equal to rho times gamma, the circulation of the vortex, times the area, like the small area of this column, right? So delta x, delta y is the area of the column. Rho times gamma, right? That's momentum, right? It is momentum because gamma actually has the unit of what? Remember, circulation is integrating velocity over a contour, right? Over a length. So it's velocity times length. Okay, so velocity times length and length, right? So it's velocity. These three things multiplied together is velocity times volume. now there is a density. It changes the volume into mass, right? So this whole thing is velocity times mass, which is momentum. Okay, so that's basically how much momentum you have on the vertical column. And today we are going to look at a we used this formula to actually calculate what is the lift on the airplane, because the lift on the plane is how much downward momentum you have in the wake, which we get the formula lift is equal to rho times the span times the circulation of these two vertices times the velocity of the flight, right? Okay, so this is for an airplane with only two vortices on the wingtip. So let's actually start by looking at a scenario where we have more vortices coming from the airplane than the two wingtips. And this is motivated by observations like this. When you have flaps down, you can see the two vortices, you can almost see the two vortices, coming not from the wingtip, but from the end of the flaps, right? This. So let's actually look at what the flow field is going to be like in this particular scenario. So here, what we are thinking is, let's imagine we have two matched pair of vortices, okay? Both pairs have a circulation of gamma, the same gamma. Let's assume the same gamma for now. And one pair comes from the tip of the extended flaps. So we have a gamma here, we have a gamma here, right? Okay. And we have also a pair of vortices coming from the wingtips. Okay, so all of them are gamma. So now let's answer the question, what is the total amount of vertical momentum in a thin vertical column of air, right, extending far up and down? So we are doing the same thing, except for in this new scenario where I have four vortices. All right. Okay, so let me just copy the formula we had before, right? So this is for one pair of vortices. Oh, I don't want to copy this. Did I select? No. Anyway, so I'm going to delete it afterwards. So I'm going to paste it over here. Actually, I'm going to paste. I'm going to delete this. Wait 1 second. I'm going to paste it and then I'll move it upwards before I delete. Okay. Anyway, so this is this is the formula we had before on one pair of vortices. Now we have two pairs of vortices. Can you figure out what is the total amount of vertical momentum in a thin column of air as a function of where you are? Okay, so this lecture we're going to start with this exercise. Please come up and see if you can figure this out. Now these exercises are getting more difficult and less routine, right? Now you have to actually think about what you have learned previously and adapt. All right, please.
Thank you.
Some of them here. Thank you. If you want colored, we have colored here.
outside these two, they cancel out, so then you get less, and then outside everything. See that?
Yeah, but also would you get these zeros like directly between them? They're all equal.
Any questions?
I think only in like the area outside is where it cancels out.
Yeah, so this is actually the first kind of conceptual questions, right? So instead of doing math, you actually have to think a little bit more, right? So it's completely okay to don't know where to start, and yeah, one of the things is that maybe think about how we derived that formula on Wednesday and see if we can use similar approaches.
Oh, I see what you're saying. So like, it's also being this about, right? Well, yeah, it's view.
Oh, okay.
What is the radius, right? Radius v over 2. So like, this is here,
I think the first question is like I think the one you read is like
So that one's sure. Right. My theory for this was superposition.
Yeah.
Like you treat it as like there's first two vortices here and then two vortices here. And you just add the solutions together. So it's
At
like,
least in the x direction.
yeah. So it's like if you were to have a straight line, and then we had these two guys pushing down like this, and then these guys pushing in another down like that, something like that, where it drops like that.
Yeah, yeah,
Would you? Oh yeah.
that's good. Why don't you write down the formula? And then answer the second question, like how much total momentum, right, you get per unit length. All right.
Okay.
right.
Yeah. Do you remember how we derived the green formula on Wednesday?
We did like the integral.
Yeah, we did the integral for just the one single vortex, right?
Yeah.
Okay. And do you remember what the result was for a single vortex? Yes, we have so the result we have for single vortex was there is a half, and there is a sign, which means it's either plus or minus 1, right? The sign of, okay, it depends on which vortex you are saying, like x minus x vortex.
That's for.
Right. So basically, depending on if x on the left or right of the vortex, this can be plus 1 or minus 1. And then this is the amount of total momentum. And now we have, on Wednesday, we have two vortices, right? For one of the vortices, we have, for the left vortex, we have downward on its right and upward on its left. On this vortex, we are the opposite. We have downward on the left and upward on the right. Which means if we are outside of this, right, we have upward, downward, and they cancel out. To the right of this, we have upward and downward, they cancel out. But in the middle, we have downward from both. So we have downward in the middle. Now can you apply the same thing here?
Yeah.
I guess right. They're still spinning in the same direction.
Like that's what I was thinking about, right? It's like this goes like this goes like this, or I guess you could make the same argument.
Yeah.
But I was thinking about, like, I was doing the X-Wing problem yesterday, and it was like how sometimes you get vortices that cancel out in like certain components.
Yeah.
And then you can just take the one like that.
Yeah.
But
So here we are doing integral velocity, right?
yes.
The integral is a linear operator. What does that mean? That means if you have two velocity fields coming from, if the velocity field is the sum of contribution from the two vortices or four vortices, right? Then you don't have to have the summation within the integral. You can integrate each one independently and sum them up. That's actually what we did yesterday when we, on Wednesday, when we looked at the effect of two vortices.
And when we got the effect of two vortices, we got just one negative gamma.
Yes, between these. I mean, the reason was that
for each, right?
yeah, for one vortex we have downward on its right, upward on its left. Both are gamma over 2. Now we have two vortices of opposite sign, so the opposite one has downward on the left, upward on the right. So if you are outside of both, we have upward from this one, downward from this one, cancels out. Only in between we have downward from both. That's why like we have half gamma plus half gamma, which
So
is
it's
gamma.
just 2 gamma. So it's just 2 gamma down.
In this case, yes, it's 2 gamma down, like 1 gamma down here, 1 gamma down here, and 0 outside. I mean, if you do the math, that's
Yeah.
okay. And
So
then
this distance is not playing a factor in the magnitude.
not in the
Because they're
magnitude,
symmetric.
but it'll play a magnitude. It'll play an effect in the second question, which is if you come over here, what is the total amount of momentum in the entire wake? Right.
So that means like
Yeah.
all directions.
That means like you have to integrate over other dimensions too, right?
Because otherwise it's
Questions?
We're making some progress now, I think.
Okay, so yeah, so it looks like you're starting from the very beginning, right? So,
We can just generally use this, right?
yeah, you can generally,
That effectively.
yeah. So
I just
this is
redefine this
bounds.
with different bounds. Yeah.
right. So this came from we go from here to here in 2 steps. One step is to figure out what is the total vertical momentum if we just have one vortex, right?
Right.
Right, and remember, like we have a half gamma on one side, also half gamma on the other side, but different direction.
Yeah.
That's from one vortex.
Right.
Okay, and then the integral of velocity is the integral is a linear operator, which means if you have the integral of the summation of two velocity fields, you don't have to have the summation within the integral, right? You can pull the summation outside of the integral. The integral of summation is equal to summation of integrals, which means we can look at the total momentum from the two vortices independently and sum them together.
Okay.
Now,
so
remember,
then
like-
we need to infinitely find it for like that one and that one, and then
Exactly.
Just add them.
And
Okay.
if we only have the blue ones, remember, like we have upward on the left, right? But because this has opposite sign, it has downward on its left.
Yes.
So if we are to the left of both vortices, the up and down cancels,
Yes.
get
that
0.
makes sense. Yeah.
To the right of both also cancels, we get 0. But in between they add up.
Okay.
Now you have 4 vortices. Figure out the addition of these. Yeah, some of you have a question. Who raised the hand?
So
Just saw anybody? No? Okay. Do you have questions? No? You figured out everything?
That's the answer.
Nice. And then what? Just to figure out the lift. I mean, the last one should be easy, right? Yeah. Do you have questions?
There's a third question.
Oh yeah. Okay, good. You also figured this out. Very good. Yeah, good. So you started from.
This is already like a.
Yeah, very good.
So,
And this is.
yeah, I mean.
I thought this was your answer to question 2 or question 1.
Wait, well, we got this, but then we read 2 and felt like that was what our answer for 2 was then.
Yes, exactly. Yes.
So what would 1 have? What would the 1?
1 is asking what is the velocity, what is the total amount of vertical momentum within a thin column, right? So you're saying it's minus 2 gamma. Yes.
So what is this?
it's saying per unit length.
Like this is mass times. Is it, I thought this
Yeah,
is
this
velocity.
is correct. Like
No, gamma's like your
the
vortex.
downward momentum
Yeah, I
is
thought
like the
this
same
right here
as
is
the.
like your
So,
velocity.
so basically, the way we figure this out is look at the contribution from the four vortices, right?
Here already like
So,
second. If you
if we're outside of these two, then they cancel out, right? This cancels with this cancels with this. If we are in between this, then all of these four add together. So each contributes half gamma, so it's 2 gamma, right? But if you're within this or within this, these two cancel out, but these two add together, so it'll be 1 gamma.
Yeah.
So that's gonna be the first.
Oh, okay. I think we got that. We just
Yeah.
didn't like kind of write that. Okay.
Yeah, good.
This is two.
Don't really know what this means though. Like this is like kind of like our mass, right? Is this our velocity or is this our momentum?
Gamma has a unit of velocity times length.
Okay.
So multiply with another b, so it's gonna be velocity times area, right?
Yeah.
Okay, and then you have density. Density multiplied by volume would be mass. So this would be mass times velocity divided by length, or momentum per length. That's the answer to the second question,
Oh,
right?
that's saying multiply v over delta t.
That's why you can
To
multiply
get-
by v to get.
like when you type
Yes, you multiply by v to get force.
CF, if you find it for 1 second, like
Yeah, very good.
divided by 1 second.
Except for lift, you need to reverse the sign, right? Because for two is the answer of how much force the air gets.
Right. Yeah.
How much force the airplane gets from air is exactly the opposite. Yes. Yeah, very good, very good. Very good. Yeah. Very good. You get the answer. You can go back to your seat. Thank you.
We were just trying to,
Grasp the intuition.
yeah, the intuition for these sections.
Yes. So here you want to these are already integrated in the z direction, right? Now to get the total momentum, you also need to integrate in this direction. This direction is uniform, right? This is the direction of the flight. So no matter where you go, you have the same velocity distribution. So that's why, like, the second question is how much momentum you have per unit distance, right? Okay, so you only have to integrate over this direction. A piecewise constant function, right? What is the integral?
You just go, over each section.
So this integral,
Yeah, the white point 3.
It's like 60% of the.
Yes, but this is minus half b, right? So yeah, so I was looking at the contribution of from the vortices, right? So if you're outside, if you're to the left of the wingtip, then you have upward contribution from this vortex, upward contribution from this vortex, downward and downward, so you cancel out. Okay. But if we are in between the wingtip and the end of the flaps, you have downward contribution from the wingtip vortex, right? And you have upward contribution from the flap vortex.
okay, so then it was just,
So maybe you can write it down. Downward, yes. For this one, it's upward, right? And for these two, they are both downward, right? So you get downward, upward, downward, downward. What do you get?
Wait, this one's downward?
Both goes that way, right? So on the left of the right vortices, the velocity is downward. No, it's this way. Yeah, we are looking at here, right, between the wingtip and the flaps.
dx dt with
Yeah. So that's why I'm saying it's 0 only when x is outside of the wingtips, right? So it should be 0.5. And all of these are correct. Just the bounds are different. Yeah. So here would be between 0.5 and the end of the flaps. Yeah, I think the problem is that you draw this location of the vortices in a different position, right? These should be exactly on the wingtip, and these should be exactly on the end of the flaps. Yes, that would be correct.
Oh wait, maybe there's no integral term. Actually, starting to
Oh, you put it as b over 4. So I think maybe I didn't say it correctly. Yeah, the width of the flaps is 60% of the wingtips.
Okay.
So yeah, so that'll be a little bit more than b over 4.
Do you want us to redo it? Or
let me see if your result is correct. I think your result is correct if it's actually half.
okay.
Yeah.
Should we leave it then, or?
Yeah, just leave it.
Okay,
It's
okay.
fine. Yeah. 1 second. You do this. Just to finish this, right? Once you add it up, you're expressing this as integrals, but you already figured out the integral. I think.
Oh yeah, you're right. So that's
Yes. Yeah. This is good for your answer to question.
The answer will look something like this, right? Or negative gamma here. Like if we're just doing this section,
Yeah.
would it just be negative gamma over 2, or would it be gamma?
No, would be negative gamma, right? That's
Oh, okay.
what you figured out.
Oh, yeah.
right?
Oh,
Yeah.
Oh, yeah, okay. I see.
And then you just go over each section.
Yeah,
Yeah, you go over each section, right?
okay.
Yeah. Okay. Okay, very good. I think most of you either just got the answer or figured out a way to get the answers, right? So the total amount of vertical momentum is going to be. Let me see what color would be best. Is going to be, first of all, they are all going downward. Would be rho. Let me just say delta A is the area of the column times gamma within the two vortices outboard. Okay, so first of all, it would be 0 if I'm looking at the beyond the wingtips, right? So would be 0 outside. And between the wingtip and the end of the flaps, the amount of vertical momentum with a infinitely long vertical column of area delta A would be rho delta A times gamma. The reason is that this vortex contribute downward momentum, this vortex contribute upward momentum, right? And both these two vortices contribute downward momentum. On this side is similar. The right vortex contributes downward momentum. The second vortex from the right contributes upward momentum, and both left vortices contribute downward momentum. All right. In between the two flaps, all the vortices contribute downward momentum, so we get twice as much downward momentum per the same unit area, right, compared to the outboard region. Okay, so now we have a piecewise constant function. That's 0 minus gamma times rho delta A, minus 2 gamma times rho delta A, and minus gamma, and 0. So to get the answer to the second question, right, we have to integrate the momentum per unit area over an area. Okay, so the area that has meaningful momentum is from the from one wingtip to another wingtip and over a length of 1, right? So if you perform the integral, you are going to get 2 rho times gamma times the length in between the two flaps, which is 0.6 b. and then plus 1 times rho gamma times the remainder of the span, 0.4b. So if you add it up, it'll be 1.6, right, times rho gamma b. Okay, and there is also a unit length in the other direction. So the unit of this is density times distance, and gamma has the length of distance times velocity, right? So there is a distance squared times velocity here. Okay, distance cubed times velocity times density would be equal to volume times density times velocity, which is the unit of mass, right? And remember, there is also a unit length over here, which makes this the amount of momentum per unit length. Okay, and finally, to get the answer to the third question, well, by the way, this is downward, so minus. And then the lift has an opposite sign. So how much momentum the air gets is how much force the airplane puts on the air, right? To get the force of the air put on the airplane, it's opposite, it's upward. So you get plus 1.6 rho gamma b times the length over which the airplane flies per unit time, which is v. So that's the flight speed. All right? Okay. We can generalize this problem. In a real scenario, an airplane is going to be generating different lift at every portion, right? The airplane, I mean, even in flight, even in cruise, when there are no flaps, the airplane has a planform that's not uniform, right? Even in cruise, when the flaps are retracted, there are more lift coming from here than from the wingtips. Okay, as a result, the airplane pushes air with a higher downward momentum in the inside portion than the outside portion. So the distribution of the vertical momentum is not going to be small, suddenly large, and smaller and zero. It is going to be a continuous function. Okay? So what is the vorticity distribution in that case? If you think about a general airplane with higher lift in the middle and lower lift outwards, it is going to generate a higher velocity in the center, slightly lower velocity, and lower velocity towards the end, right? As a result of that, think about what is going to be the vorticity in the wake that actually makes the vertical momentum has a varying distribution. Instead of varying only as a piecewise constant function, it actually varies as a continuous function. And there is actually a continuous sheet. That's why it's called a trailing vortex sheet, right? There is a continuous sheet of vortex that comes out. And for the downward velocity to be of a certain, for the downward momentum to be a certain value, right? The strength of the vortex has to be with a particular distribution that enables this downward momentum distribution. Okay, and just to look at our previous example of the downward momentum. So you have a vortex of strength gamma. If there is a change in how much downward momentum you get from here to here, right? And the strength of the vortex is exactly equal to the difference in downward momentum divided by the air density divided by delta A. Or in another sense, if instead of looking at the downward momentum, I look at lift, how much lift you get per section, right? Also what we call sectional lift. So sectional lift is basically this value divided by the delta. If I think about this direction as, for airplanes, actually the span-wise direction is usually denoted as the y direction. So if I divide this by delta y and divided this by the length traveled per unit amount of time, right? This would be the sectional lift. Oh, yes. 1 second. Sorry. Why can't I erase this? Okay. Anyway, so yeah, so the sectional lift is basically if I have a unit span, right, a unit delta B, and the delta A is equal to that unit delta B times how much I'm traveling in unit time. So that's how much the lift I get per unit span-wise direction. So that's what we call like the sectional lift. Okay, so let me just say it here. Sectional lift is basically lift per span-wise distance. Okay, it is equal to the how much momentum we get. Basically, in the previous example, right, it would be either 2 or 1, a coefficient A times rho times gamma times the area, which is the span, delta span, times the V, times how much I have traveled in the distance direction, divided by this delta span, which is equal to whatever coefficient I get times rho gamma V, right? So that's the sectional lift, how much lift I get per span. And this A, which in this case is either 0 or 1, actually depends on what is the distribution of vortices. All right, okay, and the distribution of vortices is going to be exactly how much the sectional lift is going to vary. So the circulation between two sections is going to be my delta A times this gamma. Okay, so usually what we do is we figure out the sectional lift of the airplane. I mean, we're going to look at the analysis later and next week. And then we figure out what is the circulation, right, between the different sections. And then figure out what is the wake, what is the distribution of the wake. And from the distribution of the wake, we can figure out a lot of things. Yes, question?
What is A this week?
This A actually is something I don't know, right? So I would know A if I know the circulation distribution of the vortices. Then I can actually integrate this delta A to get this A. Or I can know A if I know what is the sectional lift, right? If I know each part of the airplane wing creates how much lift, I can also figure out this A. Actually, not figure out A. I can figure out A times gamma, right? Okay, and then from A times gamma, I can get the circulation. It's basically delta A times gamma. Got it? So there are two. So basically, the distribution of A kind of connects what is happening on the airplane to what is happening in the wake. If I know what is happening in the wake, right, that is how much circulation I get, I can integrate this to get the sectional lift. Or if I know the sectional lift, I can differentiate, right, this over the span to get what I have in the wake. Okay, and once I know what happens in the wake, I can so this is no longer something you can do by hand, because usually I have so many vortices. You can integrate not just the momentum, but also the kinetic energy in the wake. And if I integrate the kinetic energy by looking at the instead of rho v, I look at half rho v squared, right? Remember, rho is mass per volume. Okay, so half rho v squared is half mv squared kinetic energy per volume. If I can integrate that kinetic energy per volume, I get how much total kinetic energy I have in the wake, which is how much the airplane has to feed, right? The amount of power the airplane has to feed to create that wake. If I have no wake, I have no lift. I'm not transferring any momentum, right? But if I create a lift, I'm creating a wake, and there is kinetic energy in the wake. Energy is conserved, the airplane has to spend some power. That's induced power, induced drag. Okay, and you can also figure out the turning force and rolling moment of the airplane by looking at its wake. So if I have an airplane that's banking in an angle, I would expect in the wake, right, my vortices goes that way. If my vortices go that way, then we can not only figure out the amount of vertical momentum distribution. I mean, it'll be exactly the same. If I look at the vertical column, right, I get contribution from this vortex. It doesn't matter the vertical displacement of these two vortices. I get the same amount of total vertical momentum per unit area. But now I can also look at a horizontal column that goes to infinity on both left and right. And I can integrate the sideways, right, momentum. And the sideways momentum is going to be 0 if it's below the bottom vortex. It's going to be 0 above the top vortex. But it is going to be non-zero. It is going to be pointing to that direction if I'm above the lower wingtip and below the upper wingtip, right? That means in the wake, I'm getting non-zero total momentum in that direction, which means the airplane is getting a lift force in that direction. This is how airplane turns, right? Like when you take an airliner, whenever it turns, it banks towards this